Hello everyone, this is Tushar. I'm going to present on NFC security and it is towards homework 8 for ECE536 Spring 16. This presentation is based on the paper Applying Relay Attacks to Google Wallet. What is NFC exactly? Near-field communication is a set of short-range wireless technologies typically requiring a distance of 4 cm or less communication. NFC allows you to share small payloads of data between an NFC tag and an Android-powered device or between two Android-powered devices. Now let's take a look at what the problem is with NFC security. Ever since the advent of NFC in phones, there have been a plethora of applications that have sprung up. Security-critical and sensitive applications have gained particular interest. For example, Google Wallet, PayPal, Square, etc. Researchers have performed analysis of various API, applications, etc. that provide payment services. A well-known issue with contactless payment cards and secure element-enabled devices is the relay attack. The practicality of relay attacks has drastically improved with NFC. A NFC signal can be relayed over two devices via Bluetooth. Credit cards are being emulated in smartphones with the introduction of software card emulation, making it possible to relay contactless credit card transactions and electronic passport transactions between two phones. Relay attack can be broadly classified as follows: as a simple range extension of contactless communication channel, or secondly as a software-based relay attack. Feasibility of software-based relay attack is what has been implemented in this paper. Now, let's take an insight into relay attack. First, let us look at relay attack by simple range extension of contactless communication. As you can see in figure 1, it requires three components: a reader device, also called a mole, in close proximity to the card under attack; a card emulator device, also called proxy, that is used to communicate with the actual reader; and a fast communication channel between these two devices. The attack is performed by bringing the mole in proximity to the card under attack. At the same time, the card emulator is brought in proximity of a reader device. POS terminal, access control, reader are examples of few reader device. Every command that the card emulator receives from the actual reader is forwarded to the mole. The mole, in turn, forwards the command to the card under attack. The card's response is then received by the mole and sent all the way back through the card emulator to the actual reader. But there are ways to prevent or hinder relay attack by simple range extension. Let's go through them one by one. First is the card's radio frequency interface can be shielded with a Faraday cage, for example an aluminum foil when not in use. The card could contain additional circuitry for physical activation and deactivation. Additional passwords or PIN codes could be used for two-factor authentication. And finally, distance bounding protocols can be used on fast channels to determine the actual distance between the card and the reader. Now, let's look at software-based relay attack. The important, or you may say the central concept behind this is to access the secure element of the device through the device application processor. through the internal interface. Physical mole is replaced here by software, or you may say a malware, on an attack device's application processor. As you may also see in Figure 2, this requires four components: a mobile phone, which is under the control of its legitimate user; a relay software under control of the attacker; a card emulator, again under control of the attacker; and a reader device, say a point of sale terminal. The relay software is installed on the victim's mobile phone. Card emulator emulates a contactless smart card in software. It has RFID NFC hardware which acts like a contactless smart card when put in front of a smart card reader. Command APDUs or CAPDUs received from the reader device are routed through the card emulator and over a wireless network, say cellular, Wi-Fi, Bluetooth, to the victim's device. There, the relay app forwards the CAPDUs to the secure element. The corresponding responses, called the response APDUs generated by the secure element, are routed all the way back through the relay app, the wireless network, and the card emulator to the reader device. A critical requirement for the software-based relay software can exchange APDUs with secure element. Now let's take a look at Google Wallet. Google Wallet is a kind of container for payment cards, gift cards, reward cards, and special offers. It consists of an Android app with user interface and a Java card applet on the secure element. The user interface is used to protect the wallet with a PIN code, to manage the payment, gift, and reward cards, select the currently active card to find specific offers, and to view the transaction history. The secure element is used to store the sensitive information of the payment, gift, and reward cards, and to interact with the existing POS reader infrastructures. The experimentation to be discussed moving forward was carried out on version 1.1 R52V7 of the Google Wallet app. Now, going a little further into the Google Wallet app. Upon its first start, the Google Wallet app initializes the secure element and installs a PIN code that is necessary for using the app's user interface. During initialization, several applets are installed and personalized on the secure element using Global Platform Card Management. Specifically, a secure channel based on the Secure Channel Protocol (SCP-02) is established between the secure element and a remote server which performs the card management through this authenticated and partly encrypted channel. Now, after successful initialization, several applets can be found on the secure element. The following is a list of applet instance identifiers, abbreviated as AIDs, that have been identified to be used by either Google Wallet during normal operation or by POS terminals during payment transaction. AID1 is the Google Wallet on-card component, which is used by Google Wallet to manage the payment cards on the secure element. AID2 is the Google MyFair Access applet, which is used to manage the MyFair Classic 4K memory of the secure element. Both applet instances can only be accessed from the application processor. Selecting them through the RF interface results in the error code 6999, denoting that the selection of those applets failed. Now, the last three applet instances are related to credit card payment transactions. AID3 is the directory definition file of the EMV proximity payment system environment. AID4 is the AID for regular MasterCard credit card. We assume that the other credit card, AID5, denotes a MasterCard co-branded as Google Wallet, but the authors have no confirmation on this. The credit card applet are only selectable while Google Wallet is in an unlocked state, otherwise the error code 6999 is returned. Access to both applet instances is possible from the application processor and also through the RF interface. Now, talking about the general commands used by Google Wallet to interact with its on-card component. First is select the on-card component. Next is the unlock command used by the wallet and allow access to the credit card application after the Google Wallet app has successfully verified the PIN. The PIN itself is not verified by the on-card component. Next comes the lock command and then the command that returns a list containing the credit card instances. Moving on to Google prepaid cards, or also called a MasterCard PayPass card. It's a credit card applet based on EMV contactless specification for payment systems. It supports max stripe mode with dynamic CVC3, uh, which is card verification code. Full EMV is not supported by the Google prepaid card, and it does not have any cardholder verification. Now, the researchers added debug output to Android's secure element API, namely com.android.nfc underscore extras. Now, this being a separate library, they modified its source and recompiled the library. They added a debug log. The debug log allowed them to monitor access to various methods of the API, also allowed them to trace all APDUs exchanged between Google Wallet and the secure element. Now, most of the data exchanged in a magstripe transaction is static for all transactions. Compute cryptographic checksum is the only APDU command response pair that contains dynamically generated data that differs for each transaction, the unpredictable number generated by the POS, and the transaction counter and CVC3 codes generated by the card. Each compute cryptographic checksum command that is sent to the card must be preceded by a fresh get processing options. Thus, the minimum sequence for generating a dynamic CVC3 is: first select MasterCard, Google prepaid card, then get processing options, and finally compute cryptographic checksum. Now, you must be wondering why the researchers selected Google Wallet to carry out the relay attack. First of all, because of its huge user base. Secondly, it is compliant, or you can say supports EMV payment standards. It can be used with any POS terminal that supports MasterCard PayPass. Android being an open source system is very advantageous as it becomes easy for the researchers to play with the Android NFC stack. Research also shows that Google Wallet is used a lot on rooted devices. Now, talking about the actual attack, the setup used by the researchers is shown in Figure 3. The attack, they prepared two things. First, a relay app, and next, a card emulator. First, let's talk about the Relay app. The Relay app is a purely Java-based Android app and is a simple TCP client that maintains a persistent TCP connection to a remote server, or also called card emulator. When the card emulator requests access to the secure element, a connection is established through Android's hidden secure element API. The app first selects the Google Wallet on-card component and sends the unlock command. This imitates the behavior of the Google Wallet app upon successful PIN entry by the user. The Relay app then listens for command EPDUs on its network interface and forwards them to the secure element. The response EPDUs from the secure element are transmitted back to the card emulator. When the transaction is complete, the Google Wallet on-card component is selected again and the lock command is used to lock the wallet. For the purpose of this experimentation, the researchers manually granted the permissions necessary to access this secure element. Next, let's talk about the card emulator. The card emulator has been built from an ACS ACR122U NFC reader and a notebook computer running a card emulation server application. Now, the ACR122U supports software card emulation mode and is available at very cheap prices. Card emulation software that is written in Python contains a TCP server that listens for incoming connections from the Relay app. On detecting activation by POS, Card Emulator requests access to the secure element through the Relay app. Then all received command EPDUs are forwarded through the network interface to the Relay app, and all response EPDUs received from the Relay app are returned to the POS terminal. When the ACR122U leaves the range of POS terminal, RF field is no longer detected. The connection to the secure element is closed. Talking about the actual attack itself, the attack prepared by the researchers was carried out successfully. They used Hypercom Artema hybrid with a VivoTech VivoPay 5000 contactless reader as their POS. Although they used a laptop, using a mobile phone is also possible and way more easy to use in real-time public scenarios. Now, how to inject the Relay app into users' devices. This, this needs integration. What needs to be done is to integrate it into an existing app and republish it on Google Play Store. Now, transaction limits are also in place on contactless transactions in many countries. So, what would the attacker do? He won't just attack a user for, say, 100 euros. What he will do is create a bot network that could attack multiple users at a given time. Communication delay is induced by the Relay app in command response transaction. Now, this delay can be countered by improving by caching all static transaction data and only transmitting dynamically generated data. Now, we have seen how the researchers carried out the software-based attack. They also devised three solutions to counter this software-based relay attack. Let's talk about each of them. The first solution talks about timeouts for POS terminals. This is enforcement of short timeouts for payment transactions on POS terminals. Example, benchmark targets specified by EMV specifications. It is easy to implement but unreliable, especially in case of shorter distances, fast communication channel. The next suggestion that they made was for Google Wallet PIN verification. This requires on-card PIN verification instead of simple lock and unlock commands to control the state of on-card components. PIN verification can be handled on-card component on secure element. In this case, the wallet's PIN would need to be known by the attacker. The third suggestion that they made was disabling internal mode communication for payment applets. Modern devices can distinguish between external and internal communication from within a Java card applet. Thus, rules for interface-based access can be applied on a per applet basis or on a per APDU basis. Capabilities could be used to disable internal mode communication for all payment applets and consequently disable their vulnerability for software-based relay attacks. The disadvantage of this solution is that the secure element cannot be used for future on-device secure payment applications. Now, let's have take a look at the consequences and conclusion. The researchers reported their findings to Google and Google acknowledged it. Google made the necessary changes to patch the vulnerabilities. Researchers again carried out the tests on version 1.6 of the Google Wallet on-card component, but the app was found to be no longer vulnerable to their designed attack. More specifically, select command to both the MasterCard credit card applet instances failed, but PIN bypassing was still possible, though, owing to simple lock and unlock commands as opposed to on-card verification proposed by the researchers. Thank you.